Thank you very much for the kind introduction. Good afternoon, ladies and gentlemen. I'm very glad to have the opportunity to speak about a specific topic that the IEA has picked up as part of its work quite recently and more intensely, because we see it as an emerging or already arrived priority in a number of countries that we have been working with more. In particular, large emerging economies, the new associate members of the IEA that have joined as part of our modernization strategy. So to name just the three big ones, this is China, Indonesia, but starting this year in March, also India. And this gave us the opportunity, the impetus to put in place a process as part of the Clean Energy Ministerial, working together with three leading countries, Denmark, Germany, and China, to form a coalition for what is called a campaign on advanced power plant flexibility. I'll say more about this campaign towards the end of my talk, also some of the opportunities that might be there for the participants here, but also organizations and companies in India working on this subject. Now, one disclaimer. If you expect a highly technical discussion about what you can do with a thermal power plant in detail to reduce its minimum generation level or its ramp rates, I will have to disappoint you. I am not a thermal plant engineer, and I will not pretend to be one. We are working very closely with them, and actually for the slide presentation that I've made an annex with some slides that we've done for technical workshops from thermal plant engineers, actually quite experienced ones, and you're welcome to consult those after the workshop. They'll be available online. So, let's start. First of all, why should we consider thermal power plant flexibility or power plant flexibility more broadly? First of all, it's in several countries, it's the biggest resource, even the ones that are pioneers of system integration. So if you look at how Spain integrates its wind and solar power with limited interconnection, in fact, it does it by a flexible operation of a fairly large fleet of combined cycle units. Also in Germany, despite the fact that also grids play a very important role, the working horse of system integration there is, in fact, surprisingly, the hard coal fleet. So even in the pioneers, they don't always say it that prominently, existing power plants play an important role. And actually, in all systems that we see today, they're a major source of flexibility. Now, when we speak about flexible generation of plants, what do we mean? We mean three things. One is the minimum generation level, which can be reached not just in case of emergency, but in terms of a routine economic operation. Then, how long it takes to start the plant. And finally, how quickly it can ramp up and down its production. Broadly speaking, if you look at analysis for system integration, the first component, so achieving a low minimum generation level, usually is associated with the highest cost savings to the system. Simply because this allows for plants to make room while a lot of wind and solar is there and to step in when it's not available, while if you do this with a large number of plants, they can collectively ramp quite quickly. Now, there are a number of barriers that stand in the way of adopting best practices for power plant flexibility. And I'll share actually two concrete examples from Germany with you just in a little bit. First, the technical solutions are often not fully understood, not known. So basically what you can do to power plants, even older ones, to increase their flexibility, to lower the minimum generation level, and so forth. Second, and this can be a tough one and sometimes more difficult, is that the regulation or market design favor running flat out. And this can take many forms. It can take the form of PPAs that are signed with independent power producers that take away the risk in terms of volume so that you promise a certain amount of generation. It can be the administrative system that was put in place. Think of China with guaranteed full load hours for coal plants. But it can also be something like key performance indicators for plant operators. In South Africa, this is an issue. So basically, you're penalized if you have a forced outage of your plant. Now, a way to avoid that is to just keep it running. So you will try to avoid stopping the plant as much as you can simply because of the incentive structure. Finally, that's something for the manufacturers. The contractual arrangements can disfavor flexible operations. So if the O&M cycles increase rapidly and impose a disproportionate amount of cost. Now, Actually, I should have updated this, the time here. The campaign was launched at the Clean Energy Ministerial, which took place in Beijing in this June, and as I already previewed, more about that at the end of the presentation. Before I go into the details, what I'd like to do first is to show how this flexibility option fits within the different challenges we face when we integrate variable renewables. Because it can be tempting to focus just on one option and because of that forget the bigger picture. Because I think keeping the bigger picture in mind is crucial in this topic, I just want to point it out. What you have here are the 6 properties of wind and solar. And I would say this is a complete list, so all of these matter, and these are the ones that matter. For the sake of time, I will bring up the full picture already. What you can see here, they are not arranged randomly, but actually they're arranged according to certain properties. First, on the left-hand side, we see low short-run cost. So once built, wind and solar produce electricity practically for free, which, when you have a liberalized market system, creates what's called a merit order effect, pushes more expensive generation out of the market. Then we see 3 properties which are actually relevant in terms of time. One is the non-synchronous nature of the generation, so that there is no direct electromechanical coupling to the grid, like you have with a thermal generator. The second is the uncertainty, so that we don't know what cloud coverage will be, that we don't know how much wind will be blowing. And the third component is the variability, so the sun goes up in the morning, goes down in the evening, and so forth. You then see how these link to different impact groups. And we see that they span from seconds or less up to many years. Similarly, when we look at the spatial components, the last 2, we have the constraints in location. It's not true that it's always far away from load, right? I mean, a rooftop PV system, you don't get much closer to load than that. But you can't haul around the primary resource. So there's a constraint in location. And finally, the point in modularity. So we have small units that can be assembled to very large plants if you want, but that can also be used in very, very small applications. What you see is we span a very wide range in timescales and a very wide range in geographical scales. Now, as a physicist, one thing that I find fascinating here is that these timescales and length scales are actually coupled. So a lot of the simplifications that you have in describing nature is that you can disregard these couplings, but it's not possible when we look at system integration, which makes it tough to crack, but also very interesting. Now, here I highlighted 2 areas with 2 colors that show where we see power plant flexibility as making a critical contribution. And the red one is the problems that they solve, and the blue one is where they might get into trouble. So on the red side, we see stability, reserves, balancing short-term changes. That is something that in the immediate term, conventional power plants are being used for. Also, when we look at abundance situations, when there's a lot of wind and solar, to ramp down and make room for wind and solar. So in the short term, make room while keeping the lights on. In the long term, it is about bridging longer periods of scarcity, which cannot be covered well with other options. You know, demand-side response saying, okay, please turn off if there's a week of very low in-feed, for example. That's not something that people will embrace. And then you see this blue area, which is the asset utilization. So essentially, as you become more flexible, you become a part-time worker. The amount of energy over which you can spread your fixed cost is reduced. So this has commercial implications for the plants. We then have a scoring system for the different flexible resources. I won't go into it in detail. Again, this might be of interest when we look at the documentation of the conference. I'd just like to point out one thing that I find quite interesting, because it's a difference between the long and the short term. In the short term, they're very effective. Dispatchable generation is very effective at avoiding surplus because it can back down. But once you reach the point where you cover nearly 100% from wind and solar, you need different options to deal with challenges. Okay. Now, what I'd like to do for the remainder of the presentation, I'll mention one cost-benefit analysis that we've done at the IEA already in the past, concrete examples of retrofits that have been done, and then speak a bit about the regulatory and market design possibilities we have to incentivize power plant flexibility before closing on the campaign. What you see here is a somewhat older modeling that we did for a 2014 publication, where we already included the idea of a more flexible operation of plants. And now this is truly a coincidence. We assumed 70% in our baseline scenario for thermal plants, and then looked at what does it bring to reduce it to 50%. So quite conservative numbers, actually. It's a system designed as an island, but the size of Germany, with a penetration of 30% or 45% of wind and solar. And what you see is that it is cost effective to perform these retrofits, but it is sensitive on the costs associated with this. And I would say this is one area where we need more transparency, where it has to become clear what different interventions cost. Of course, these are highly plant specific, but I think getting a better understanding of what drives differences in costs is quite crucial. If you look at these numbers, they're quite close to what is currently cited in China. However, if you look at the study that was done by Agora Energie vendor, or for Agora Energie vendor in Germany, they have about an order of magnitude higher costs. Now, I spoke to some people from the industry, and they basically mentioned, okay, this is probably an overhaul of an older plant that includes additional measures. So just as a word of caution as we interpret these figures. Now here, two retrofit examples, real-world cases. To the other manufacturers, no offense, these are examples from Siemens. There are also examples from GE, Hitachi, Mitsubishi Heavy Industries. But I think it's quite impressive. If you look here, these blocks are old lignite plants. Yeah? So we're not talking even about hard coal plants, but quite old lignite-fired generation. And if you look at the minimum load that was achieved in each unit, it was reduced from 440 to 290 megawatts, and proven results 270. And we see that we have more than a doubling of the achievable load gradient. It was also possible to reduce the startup time and increase the efficiency of the units. And actually, they are now operating sometimes in double shift operation. So they've really gone from a baseload plant to a flexibility resource in the German system. On the right-hand side, you see another plant where the minimum output was reduced to 20%. But somebody told me, Simon, be careful with this result, because actually the plant will be taken off the market, if I'm rightly informed, because of economic challenges. So also here we see making the economics work out for plants is not trivial. In going about improving the flexibility of thermal generation, we spoke quite a bit with people who did this in Denmark. I would say Denmark is the first country that really underwent systematic retrofit of its plants. And here, it's not just about looking at the optimization of the individual unit, but it's also how this fits in the overall power system, and most importantly, the use of digital monitoring and control equipment. A lot of the interesting examples that you find for example, improving part load efficiencies are associated with better monitoring of what's going on. I'll give you an example. If we look at the burner of a coal plant, usually the oxygen concentration is measured outside of the area where you actually have the combustion, where you have the flames. And if you part load the plant, you don't really know what's going on with the combustion process. So an update that is possible is to put in a laser sensor that measures the flame temperature directly in the combustion zone and will dynamically adjust where the oxygen goes to have a smooth oxygen concentration across the combustion zone, even at part load. These are the kind of things that allow you to get to higher part load efficiencies, for example. One additional slide here on what China is doing in this. I think it's important to realize that a country like India is not alone in the question of improving thermal power plant flexibility. I think it's an issue that is coming up in other countries as well. And in its 13th five-year plan, China actually has a target of retrofitting 20% of its installed coal power plants to become more flexible. In particular, the focus is on combined heat and power plants. So to make sure that as they serve heating loads, also in wintertime, you don't have to curtail wind and solar during those periods. In implementing the strategy and speaking to the Chinese, they say, well, we still can extract a lot of flexibility through operational improvements, improving the market design regulation, but this is really a forward-looking measure to say 5 years down the road, we will need this if we really want to maintain ambitious growth trajectories. Okay. Final area is how can we incentivize flexibility? And maybe this is a good opportunity to mention we'll have a workshop that also looks at technical but market design aspects to see some of the best practices in Europe. But essentially we can categorize by carrots, sticks, and some other tricks. So one is to actually provide an incentive to leave the market. For example, to introduce something like a regulation service that if you reduce your output below a certain level, you get extra money paid for that. Yep? So essentially paying somebody to leave the market. You could also say that you give priority dispatch to other resources to push generation to become more flexible. There can be also tricks done by the system operator. Take the case of Ireland. The Irish system operator announced that they would give priority during the night to keep online, they have to keep online a certain number of units. And they said, we will keep those units online that report a lower min-gen. And what I've been told is that the large coal power plant in the country, it's called Moneypoint, went from reporting 90% min-gen to 60% min-gen practically overnight. Yeah? So these incentives matter as well. Last example on the economics. What you see here are the 30-minute spot prices in South Australia on a day where South Australia was craving flexibility. And I'd like to draw your attention to the market prices between 10:30 and 11:30. We see the price is 9,000 Australian dollars per megawatt hour in 1/2 hour. It then turns negative for the next half hour, and then goes back up again to 65 Australian dollars. Now, this should immediately make the point where it can be nice to have a flexible plant, right? You want to be there when you're making incredible amounts of money in half an hour, and you want to get out of the market when power generation is seen as basically garbage production and you have to pay for its disposal. So having volatility on spot markets can actually also be a way to incentivize flexibility. All right, I've reached the end of my time, luckily also the end of my presentation, with the final slide here on this campaign for advanced power plant flexibility. You see logos of the companies that are joining, also the countries that are participating. In India is one of these countries. Very briefly, we'll be doing 3 things as part of this campaign. One is high-level policy fora to really create the political backing for this. Technical workshops to understand better the market design and the regulatory interventions, what you can do technically. And third is study trips, so that you can actually see how this has been done in practice. The first round of study trips is coming up in Germany in the beginning of November. And if you're interested in this, just drop me a line. My email address is just first name, last name @iea.org, and we'll be very happy to see what we can do for you in terms of this very interesting topic. Thank you very much.